All right, welcome to another explainer. Today, we are tackling what is honestly the greatest mystery in the entire history of science. We're going inside the atom. I want you to imagine a perfectly locked puzzle box. It's so incredibly tiny that you can't even see it, yet it holds the key to literally everything in the universe. Everything. And you know, it actually took humanity over 2,000 years of guessing, experimenting, and some truly brilliant deductions to finally pick that lock. So let's dive in and see exactly what's hiding inside.
So, what is everything actually made of? It's a massive question, right? And well over 2,000 years ago, long before we had microscopes or any fancy lab equipment, some pretty brilliant minds were already obsessing over this. Over in India, the philosopher Acharya Kanada imagined this tiny, unbreakable particle that he called a parmanu. Meanwhile, ancient Greek thinkers like Democritus were proposing a very similar concept, calling it atomos. Honestly, these were mind-blowingly intuitive guesses for the time. But without technology, the puzzle box stayed firmly shut for centuries.
And we're talking about a massive jump in time here. From those ancient guesses around 500 BCE, we actually have to fast forward all the way to 1808 before John Dalton steps up with the very first scientific atomic theory. He pictured atoms as these solid, completely indivisible building blocks of matter. But you know how science is? It's completely relentless. By the time we hit the turn of the 20th century, experiments by scientists like J.J. Thomson and Ernest Rutherford were about to prove Dalton's theory entirely wrong.
Okay, so the first real crack in our locked puzzle box actually came from electricity. Back in 1897, J.J. Thomson was messing around, shooting electricity through these gas-filled glass tubes. And he noticed something super weird. These mysterious rays were being heavily drawn toward positive electrical fields. His massive light bulb moment? He realized these rays weren't just energy, they were actual streams of unimaginably tiny, negatively charged particles. We know them today as electrons. And because these little guys were coming from inside the atom itself, well, Dalton's whole indivisible block rule was totally shattered.
Now, Thomson knew atoms were electrically neutral overall. So if there are these negative electrons running around, they absolutely had to have a positive counterbalance, right? So he came up with this brilliant analogy. He basically imagined the atom like a watermelon. Think of a soft, squishy sphere of positive energy, that's the red pulp, with all those negatively charged electrons just scattered throughout it, kind of like the seeds. It was a really elegant guess, and it perfectly balanced out all the charges.
But here's the thing about science. Every time you answer one question, you basically breed three more. If Thomson's atom was actually this soft, squishy watermelon, what on earth would happen if you shot something incredibly hard and fast right at it? Enter Ernest Rutherford. He designed this frankly brilliant experiment where he fired dense, high-speed, positively charged alpha particles straight at a microscopic, ultra-thin sheet of gold foil. Now, based on the watermelon model, Rutherford totally expected these heavy alpha particles to just tear straight through those soft gold atoms like a hot knife through butter. But, plot twist, the results were absolutely staggering. While most of the particles did pass right through, some were violently deflected off to the sides. And incredibly, literally defying all their expectations, a tiny fraction of them bounced straight back. Rutherford was completely floored. He later said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce right back to hit you in the face. No way, right? To make sense of this crazy rebound, Rutherford realized something massive. The watermelon theory was dead wrong. There had to be a remarkably dense, positively charged core hiding right at the dead center of the atom, the nucleus. But here's the kicker. It is shockingly small. To put this into perspective, if a single atom were the size of a massive cricket ground, the nucleus wouldn't be the size of the pitch, or even a cricket ball. It would be a single, tiny grain of black pepper sitting right on the center line. Literally everything else in the atom is just dead empty space. So Rutherford updates the model. He proposes this planetary system. You've got this dense, positive, sun-like nucleus in the middle, with negative planetary electrons orbiting around in all that vast empty space. Makes sense, right? Well, hold on. There is a completely physics-breaking flaw here. You see, an accelerating charged particle, like an orbiting electron, should constantly be losing energy. And if it's losing energy, it should spiral inward and just crash straight into the positive nucleus. If Rutherford's model was exactly right, literally all matter in the universe should instantly collapse. So, what were we missing?
Enter Niels Bohr. This guy essentially solved the whole collapse mystery by dropping a brand new rule on everyone. Electrons do not just orbit randomly wherever they want. They're actually locked into these very specific fixed circular paths, which he called stationary states or shells. And the magic here is that while an electron stays in its designated shell, it doesn't lose any energy at all. Zero energy loss means zero collapsing. Oh, and fun fact, they named these shells K, L, M, and N. Why start at K? It was actually just a quirky holdover from some early X-ray experiments, and the letters just kind of stuck.
All right, so now we've got a beautifully stable model that doesn't collapse. We're good, right? Nope. Scientists immediately slammed into another incredibly frustrating math puzzle. Think about this. Hydrogen has 1 proton. Helium has 2 protons. So logically, helium should be exactly twice as heavy as hydrogen. But when they measured it, helium was actually 4 times heavier. There was this massive amount of phantom mass hiding inside the nucleus that protons alone just couldn't explain.
It took until 1932 for a scientist named James Chadwick to finally find that missing piece, the neutron. It's a particle with almost the exact same mass as a proton, but it has absolutely zero electrical charge, completely neutral. These guys are the heavy lifters of the atom. Not only do they perfectly explain all that missing phantom mass, but they also act as this crucial buffer. They literally space out the positively charged protons inside the nucleus, so those protons don't violently repel each other and blow the atom apart.
Okay, let's take a quick breather and look at the whole cast of our puzzle box. We have 3 main characters. First, the incredibly light, negatively charged electron zipping around on the outside. Second, the heavy, positively charged proton locked right in the center. And third, the equally heavy, neutral neutron sitting right beside it. That's the whole shebang. Literally everything you see around you, your phone, your dog, even yourself, is just built from different combinations of those exact 3 particles. Now that we've finally cracked open the physical structure of the atom, we run into a very human problem. As scientists started discovering more and more unique combinations of these particles, which we call chemical elements, how on earth were they supposed to talk to each other about them? Science is a massive, global effort, so we desperately needed a universal language that everyone, everywhere, could easily understand. Back in 1803, John Dalton actually tried drawing these little pictorial symbols for the elements. But as the discoveries kept piling up, memorizing dozens of tiny drawings became completely impossible. The brilliant, and honestly much simpler solution, just use the alphabet. Today, every single element gets a globally recognized 1 or 2-letter symbol. Hydrogen gets an easy H, cobalt is Co, and sometimes it gets a little quirky. Iron is Fe because it comes from its ancient Latin name, ferrum. But along with those letters, we also use 2 incredibly vital numbers to identify elements. The first is the atomic number, also known as Z. This is super straightforward. It's literally just the exact number of protons in the nucleus. Think of it as an element's ultimate ID badge. Got 1 proton? You are absolutely undeniably hydrogen. Got 6? You are carbon. If you change the number of protons, you literally change what the element is. And in a neutral atom, this number also perfectly matches the number of those orbiting electrons. The second vital number you need to know is the mass number, or A. Again, super simple math here. You just add the protons and the neutrons together. Notice how we completely ignore the electrons? That's because they are so unbelievably tiny and light compared to the nucleus that their mass is basically non-existent. It's totally negligible. When it comes to weight, the nucleus really is doing all the heavy lifting.
So we have the heavy nucleus locked down tight in the center. But what about all that massive empty space outside, the rest of the cricket ground from our earlier analogy? If an element has, let's say, 11 electrons, how do they actually arrange themselves into Niels Bohr's specific shells? It can't just be a free-for-all, right? What are the strict architectural rules for building in this microscopic space?
Turns out, the golden rule for building an atom is actually a pretty simple mathematical formula, 2n squared, where n is just the shell number. So the very first shell, shell 1, holds a strict maximum of exactly 2 electrons. The second shell, shell 2, can hold up to 8. And the rule here is absolute. You must completely max out the inner shell before you are ever allowed to start building out into the next one. You work from the inside out.
Let's actually see this rule in action. Look at hydrogen. It's only got 1 electron, so it just pops right into that first K shell. Easy. Helium has 2 electrons, which completely fills that inner K shell to its absolute max. But then look at lithium.
Lithium has 3 electrons. It drops its first 2 into the K shell. But because that shell is now totally full, that third electron is literally forced to open up a brand new outer shell, the L shell. It's like filling up rows in a movie theater. And with that beautifully ordered blueprint, we finally have a working model of the atom. I mean, think about it. We went all the way from ancient philosophers just dreaming about invisible dust to mathematically mapping exactly where electrons orbit a dense core. But, as always, science never actually stops. The neat, tidy Bohr model eventually gave way to the deeply bizarre, mind-bending quantum mechanical model. And even more terrifyingly, if that tiny nucleus is bound together by these immense, invisible forces, what happens if we decide to forcibly smash that puzzle box apart? Well, that question dragged humanity right into the atomic age, and that is a wild mystery for our next explainer. Keep questioning everything, and thanks for exploring with us today.